Hello, dear colleagues. My name is Jan and I represent my working name since my last and strategy control considering intelligence and speaking. This work was developed in conjunction with the professors Paulo Marques Jacquiard, Cecília Leão, and Leonardo, with support from the Robotics and Rehabilitation Laboratory at the Federal Institute of São Paulo. So the hand is one of the most complex piece of natural engineering in the human body. It allows both a manipulation with great precision and a strong grip. But unfortunately, some people cannot take the advantage of the hand movements either because they don't have enough power and coordination or because they don't have the hand or the arm. So the upper limb process rejection rate is about 17%. It means that in a group of 10 patients, for example, that starts to use upper limb practice, that stops using it or uses it correctly at the beginning of the rehabilitation process. So the present work brings a new approach to hand practice that considers the stiffness and the arcos of the hand to allow an intuitive grasping process. The hand great precision movement is not focused on the work but the grasping process of the use. Because in a daily life when somebody grabs an object, usually it is not necessary to be concentrated on the step. A practice that allows the subject to grasp most objects without great concentration for this step. So in the experimental methodology, the first stage uh, was the mechanical development of the prototype. According to Carpentry 2000, when you want to pick up a bulk object, the hand adapts as much as possible to its shape. In this case, the hand is excavated and knuckles are formed oriented in three directions: transversely, longitudinally, and obliquely. So in this picture, we can see the relationship between the arcos of the hand, the arco applied in the prosthesis model, and the arcos present by the theory. In this picture, we can see the 3D model, the prosthesis projected in a 3D software. In this picture, also in the inside the experimental methodology, we can see arcos of the hand in a comparison. All right. The first, the arcos of the hand in the mechanical processes and comparison with the arcos of the hand, the human hand. Generally, the prosthesis in Mercury uses two or three myoelectric sensors placed in the arm. They are connected to the control circuit by wires. The chosen bracelet has eight EMG sensors and transmits the signals captured by wireless communications on Bluetooth interface. The use of the proposed bracelet brings a more adjusted fixation to the patient's arm. So the control schematic for the movements of the process, we can see that the bracelet used in this case is responsible for the capture, transmit, and transmission of the myoelectrical signals. These signals are transmitted to a Bluetooth interface connected to the microcontroller, which, according to the program that is submitted, performs motor control, and consequently, it results in a flexion movement and an extension movement of the process. So, in the step of the specific stiffening applied to the phalangeal joint, in a joint mechanism, the stiffening determines the strength of the force to be applied internally or externally to make possible a certain spacing. In this case, the stiffening is applied to the joint system of the fibrin so that the flexibility is attenuated. The attenuation of the flexibility that is increased stiffness is analogous to the stabilizing function of muscle acting on a joint. So the stabilizer function is a natural action of a muscle to stabilize a body part against some other force that is their action. That force can be internal and external. The control of stiffness applied to the interphalangeal joints of the prosthesis is performed in a passive or a natural way. So the passive stiffness is implemented through the application of elastic cords that run along the length of each finger of the prothesis, both in the palm and the dorsal region. Um, when the cables are pulled so that the fingers perform the flexion movement, the elastic cords applied in the dorsal region act as a stabilizing muscle in its function. So the same happens in the extension movement. The kinematic was studied with different intensity of the stiffness which was obtained using different kinds of elastic cord. So the elastic cord responsible for passive stiffness in the front can be seen in this picture. The cords were chosen instead of fractional metal springs due to their higher tension radius and higher range of motion. In addition, the cords are easily attached to mechanisms and stiffness can be increased or decreased by size, simply adding or removing the cord. The cord used in the product is made of a natural rubber. The material elasticity constant K was obtained through traction tests performed inside a laboratory. So according to Brooke's law, the constant K is 20.66. So the modulus of the elasticity E, also known as Young's modulus, is a mechanical parameter that also provides the stiffness of a solid material. According to Ashby, 2012, um, the Young's modulus of natural rubber is reported at value being 0.0015 dPa and 0.0025 dPa. The Young's modulus found the elastic cord applied in this process is 0.002094 dPa. So, according to these parameters consolidated, it was possible to find the values of the things applying to the each finger. So, the elastic cords are subject to the force when they play the whole of the agonist muscle. At the same time, the submit force increase in stiffness, thus playing the whole as an antagonist muscle and made as a stabilizer muscle. So with your working terms of the process defined, it was possible to graphically illustrate the relationship of movement in both to the movements of the extension and flexion. So according to how 2005, in the human hand, this was the length tension relationship of the muscle. The total tension present in an extended muscle is the sum of the active tension provided by the muscle fibers with a passive tension provided by the muscle tendons and members. So active tension is the force by the muscle and passive tension is the force suffered by the muscle. Um, the head process was tested just inside the laboratory, but the tests showed that the process valued the patient instinctively grasped diverse objects with different shapes and daily tasks. It confirmed the benefits gained from interphalangeal techniques and hand prosthesis shape considering the arcos of the human hand. That leads easier and secure grasp. The test revealed an easier way for grasping a variety of objects, especially if you compare it to the most common myoelectric prostheses used around the world. In this picture, we can see some grasp tests. So the prosthesis grasping a bottle of water, grasping a pen, grasping a table, tennis ball, for example. So as the conclusion, the mechanical model behaves as expected, especially when combined with convenient stiffness alteration. The application of passive stiffness through the elastic cord in the interphalangeal joints proved to gain important features. The test performed showed the practice is more useful in the process of grip with objects considerable dimensions and more volume. So it is advisable for the best approach to use the product combined with a silicone commence code. So the stocks and the tests showed easier control of the product. So this is This was my work and appreciate the opportunities and thank you.